Okay, intervals of increase, decrease. So for our function, ln of x squared minus 1, our derivative will be 1 over the argument multiplied by the derivative of the argument. So then we will have to think about setting that equal to 0 to find our critical number. So really we have 2x on. We could factor that bottom if we wanted to, or leave it as x squared minus 1. Okay, so when would this be true? We're finding our critical numbers here. So remember, we could do this numerator and denominator separate. So 2x is equal to 0. X would then be equal to 0. Notice that's not in my domain. So think back to this domain that we had. We had x had to be greater than 1 or x has to be greater than negative 1. So this guy's not in my domain. And then what about the second piece? So you could look at it from the x squared minus 1 is equal to 0 and then factor it, or you could look at them separately, however you decided to do that. You would get that x is equal to plus or minus 1, which are also not in the domain because those are my vertical asymptotes. So what does that mean? We have no critical numbers. However, we still need to do some analysis to see what's happening with our graph. Is it increasing or decreasing on either side of those asymptotes? Now, our limit answer probably gives us the information on that, but let's do the analysis work to confirm. Okay, so let's do our little number line. And I'm going to go from negative infinity to negative 1, positive 1 to infinity. And I'm going to just block off this part because that doesn't actually exist on my function. And I may even choose to do like little vertical asymptotes in here, right? However you decide to do this, just to remind yourself that negative 1 and 1 are actually not part of my graph. Okay, so let's test something between negative infinity and negative 1. Let's just test negative 2 and positive 2 and see. What does that do if I put it into my derivative? Okay, so if you put negative 2 into your derivative, 2 times negative 2 is negative 4. X, so negative 2 minus 1, negative 3. So I got two negatives. And then I got negative 2. That's also a negative. So 3 negatives in those factors is going to give me a negative piece in here. And then what happens if I put in the positive 2? The numerator would be positive. 2 minus 1, that's positive. 2 plus 1 is positive. So I have 3 positives. So everything is positive. That's a little sloppy. And so what does that tell me about my function? It tells me it's decreasing and then increasing. However, there is no max happening, or min actually, because of the way it's going, because we have those vertical asymptotes. Okay, there's a big giant space in between here. So make sure that you pay attention to that piece. So that makes step 6 easy. There's none. Or no max min. We could be formal and talk about our proper intervals. So we could say, therefore, f of x is increasing from positive 1 to infinity and decreasing from negative infinity to negative 1. All right, so step 7 will be our second derivative to determine our concavity and do we have any points of inflection. So what do we know? We know that our first derivative was 2x on x squared minus 1. And now I want to take the derivative of this. I'm going to use my quotient law. You could bring your x squared minus 1 up and do product if that's your preference. Okay, so second derivative, low, d high, less high, d low, Draw a line and down below, squared shall go. There it is. And then can we tidy this up? Let's see. We could factor out a 2. What would we be left with? We'd have x squared minus 1 minus 2x squared on x squared minus 1 squared. And then that's going to leave me with negative 1 minus x squared on x squared minus 1 squared. We could then pull a negative out of that. So let's see, negative 2 x squared plus 1 on x squared minus 1 squared. Whew! Okay, so there's my second derivative. And if I set this equal to 0, we're going to then look for significant numbers. So let's think about this. The numerator, negative 2x squared plus 1 is equal to 0. So divide out your negative 2. You've got x squared plus 1 is equal to 0. Then you have x squared is equal to negative 1. That's not going to give me any significant numbers. That's impossible for that. So there's none out of that. And then the other one would be x squared minus 1 squared is equal to 0. Well, this one we've seen. So we have x squared minus 1 is equal to 0. We have x is equal to plus or minus 1, which is also not possible because those are my vertical asymptotes. So therefore, we have no significant numbers. But again, we still want to do our analysis work because we want to see what is happening. So let's see. Negative infinity, negative 1, positive infinity. And then I'm going to block off that middle just to remind myself it can't happen in there because of my domain restriction. So let's test our negative 2 and our positive 2 again and see what is happening in our second derivative. So our second derivative, if I think back here, we have x squared plus 1. That's always going to be positive because whatever you square, then you're adding 1. The bottom, x squared minus 1 is then being squared, so that's always going to be positive. So that just leaves you with a negative 2. So the second derivative, in fact, is always negative. It doesn't even matter that I have test points. Okay, so what does that tell me about my graph? It tells me I am concave down for the entire thing. And again, it's not possible to have points of inflection due to the restricted domain. We have this big gap in the middle there. Okay, so what do I know? That f of x is concave. Well, it is better to not write shorthand on this part. Concave down. And you need to use your restriction, negative infinity to negative 1. You cannot say it's happening for all reals because we got a big gap in the middle there. Okay, so don't forget about the gap. Okay, now we get to graph it, and I have no space left to graph. Whew, okay, let's see how squishy we can get. All right, so here is our sketch. What do we know? This is where you should do better planning. Okay, we have a vertical asymptote at x is equal to negative 1 and x is equal to positive 1. We have x-intercepts happening at root 2 and negative root 2. The graph is heading towards negative infinity when you head towards your vertical asymptotes from each direction. And it is, let's stick with the green, going concave down on both sides. So you should see symmetry there. That's not the best symmetry for my graph. But you can always throw that into your graphing calculator and have a look. I threw it into Desmos just to make sure we got the right idea. And here it is, ln of x squared minus 1. So we nailed it. There it is. Okay. Last question. Find all points at which the graph of f of x equals x ln x cubed has a horizontal tangent line. Okay, horizontal tangent line is going to tell me my slope has to be 0, which means my first derivative is equal to 0. Okay, so let's start with that. Find the first derivative. So we have a product rule. So 1 d2. So if I take the derivative of ln x cubed, I'm going to do a chain. So 3 ln x squared. Derivative of the inside is 1 on x. So 1 d2 plus 2, which is your ln x cubed, d1. Derivative of x is just 1. What could we tidy up in here? So it looks like my x's could cancel here. And then what do I have? I have 3 ln squared x plus ln cubed x. I could factor out a ln squared, and I'd be left with 3 plus ln x. And what do I know about this? This has to equal to 0 if I want it to be this horizontal tangent line. So step 2, I'm going to set this equal to 0. And then I'm going to leave this in factored form because this is easier to solve. So if ln squared is equal to 0, how do you go about solving that? We want to find these x values where this is happening. So let's flip this into log base e of x. Let's first of all take the square root of both sides. That makes it easier. And then we would have log base e of x is equal to 0, ln x is equal to 0, so e to the power of 0 is equal to x. So one of the x values is 1. And then in the second case, we have 3 plus ln x is equal to 0. So let's isolate. Ln x is equal to -3. Again, remember that ln, and you don't have to flip it every single time. You'll get into the habit of not, but I like to put it in for notes. And then let's convert. E to the -3 is equal to x. So the other x value is this funky 1 on e cubed. And now we need to find the y values for these x's. Where are these points happening? That's the question, right? So then I just need the y values and I'm done. So let's grab a new piece of paper here. Okay, so step 3, we're going to find those y values. Oops, if I can spell right. So if x is equal to 1, what will the y value be? So I need f of 1. So 1 times ln 1 cubed. Okay, so remember that our function was x ln cubed x. Okay, so what is this? What is ln of 1? Think about this as a log. Okay, this is just 0. 0 cubed, 0. So I have 1 point happening at 1, 0. And then let's do the second one. Oops, I can't keep my notation the same today. At x is equal to 1 on e cubed. So I'm going to do that, 1 on e cubed into my function. So 1 on e cubed for x. And then I have ln of e to the -3 might be better. This whole thing cubed. I'm going to put that -3 in the front. And so I have -3 of ln e. Remember, ln e is just 1. So 1 on e cubed, -3. So this is just 1. And -3 cubed is -27. So therefore, we have a point happening at 1 on e cubed and -27 on e cubed. Whew! There we go. We finished just before the video is going to end. There's a U-try. I'll throw up the solution after the video ends here, and you can see if you can get the answer to match. All right, one more lesson in Chapter 8, and we are done.